Yeah, so that's actually going to be an easy one. Let's say we had, let's get that in there. So, what did it equal? -4. Okay. So you start out with y cubed plus y squared minus 5y minus x squared equals -4. Was that it? -4? Yeah, -4. Okay, sweet. So with implicit differentiation, you're sort of keeping this extra y prime. I'm going to say what that is. In his example, what he wrote was dy over dx. When I learned it, we just said y prime because it was faster to write, and it means the same thing. These two are strictly equal. So what you do is you take the whole equation and you take a derivative of it, kind of every part of it. So the thing is with what you do with the y's is that you tack on this y prime after you take the derivative. It's sort of like a way to go back and forth. Kind of like if I were to factor, say, 5x plus 25, if I went down and factored it, I would have 5 times x plus 5. And so there's kind of this equality I can go back and distribute to get back to the 5x plus 25. There's an equality that's kind of preserved. Sometimes what happens when we do derivatives, if I just say x squared and take a derivative of it, that's just 2x, but these two things are not equal. But if I were to say x squared, and then I implicitly took the derivative on x, then this would equal 2x dx dy, which later you'll learn how to take an integral, then these two things will be equal. So that's kind of the reasoning for that. It's to preserve equality. Anyways, okay, so now we're actually going to do it. So what I'm going to do is take the derivative of this whole thing, dy dx, because we are doing it on y. So I'll say the derivative, I'm going to distribute this derivative because I can do that. All these things are being added. So this will be 2y squared. I'll just say y prime plus 2y. Again, I'll multiply by y prime minus 5 times y prime. And then, let's get rid of this junk. Okay. That's 5y minus 2x equals 0. So now my objective is to solve for what this y prime is equal to. And so what I'm going to do is first take this negative 2x and add it to both sides of the equation. So here I'll add 2x, add 2x. So now I'm going to have this left-hand junk. And then on the right-hand side, I'm going to have this equals 2x. So what I'll do from here is I'm going to factor y prime from each of these terms, and kind of like in the same way that I was doing that 5x plus 25 before. So this will be y prime multiplied by 2x. I'll have the 2y squared plus 2y minus 5. I'll divide both sides of this equation by that little piece right here that's in white. Copy and paste that. And copy and paste it over here. So now, when I divide these two, well, anything divided by itself is 1. So this will be y prime is equal to 2x over 2y squared plus 2y minus 5. All right, and I hope that's the same solution. Let's see. Yeah, okay, cool. And that's exactly what he got. So yeah, that's the kind of the crux of it. Oh, maybe also let me kind of recap what we've done. So with implicit differentiation, you're sort of maintaining this path to get back to what you originally started with, notating that you have y prime. Later, you'll learn the integral, which is this symbol like this. It looks like this weird S. Maintaining y prime is an indication to the reader, hey, I didn't just say x squared equals 2x. No, what I said was x squared is equal to 2x dx dy. If I was implicitly differentiating on x. Yeah. So what this does is it preserves the equality of mathematics in the same way that if I had 5x plus 25, I can't just say that's equal to x plus 5. That's not true. I would have to say 5x plus 25 is equal to 5 times x plus 5. I achieved this by going this way as factoring, and this way that's distributing. So too, is this the same way? In this direction, it is differentiation. In this direction, it's integration, which again, the integration part you'll learn later. Yeah, so that's the reasoning.